All right. So if you've ever tried edge computing, it's got its own complexities. And if you try to add an ML, machine learning, or computer vision to that, it gets even more complicated. This is the story of myself and a coworker as we took on a project that became a little bit more cutting edge than we expected. And it's going to force us to learn some skills in some new areas, because we're not DevOps engineers and we're not machine learning experts, but we are solutions architects, and we love a good challenge. This story is going to cover some of our successes and some of our failures, but it's also going to cover the design of an edge computing platform, as well as the integration of computer vision into that at the edge. My name is Jason Barbee. I'm a solutions architect at C-Spire. My coworker is Jeremy Sanders, and due to some previous travel arrangements, he was not able to come to the event. And I've been in the industry for 20 years, and this is definitely one of the more exciting projects that I'm happy to share with you at DevOps Days Birmingham. Our agenda for today, we're going to talk about the truck so that you understand what features we're trying to solve for. Why edge at a truck? We're going to talk about edge computing, ask the question, why edge computing, and what does it need to do? And then we're going to move into a little bit of the machine learning side, and you're going to see the real world impact as we integrate computer vision to this project. And it's going to impact everything from hardware to DevOps. And last, we're going to talk about edge support, because it's a lot different than the cloud. You can't just Terraform your way out of it, right? So I'm going to show you some real world stories around that. This is the truck that we're working on. This is the Alabama Department of Transportation ASAP fleet. Their job is to patrol the metro Alabama areas and help keep traffic moving safely. That might mean helping you fix a flat tire while redirecting traffic around you, or being at the scene of an accident or construction zone area. And our truck story really begins with data silos, because there were already some systems on the truck, but they were locked up by the vendor's APIs. So for example, there was a fleet management with GPS and OBD2 data. So they wanted to get to that data, but it was locked behind a vendor. They wanted to control the sign on the back of the truck. It's very inconvenient for the driver to have to walk into the truck cab and type out a message to display. So they asked us, how can we make these trucks smarter? So an idea begins to form, the plan shapes up, and it's a communications platform with dual cellular connectivity, streaming OBD2 data in real time, as well as storing that for predictive maintenance in the future. Taking GPS data and funneling it to the traffic management systems that need it. And remotely controlling that sign on the truck from the traffic management center so that they can communicate to the oncoming traffic. As well as 5 cameras, 1 on the inside, 4 on the outside, and at least 2 of those cameras looking for infrastructure analysis. Our first use case is Guardrail, and more to come. Guardrail damage. Why guardrail damage? Well, it's a safety issue, but it's also extremely tedious to log the damage, because by the time you think you saw the damage, it's already hundreds of feet behind you, and you don't know exactly how bad it was. So we also lack the vocabulary to actually report that to the proper authorities. It's very difficult for a human to understand, to say low, medium, and high. I have the luxury of having many different pictures of guardrail damage to show you today. So our goal in this is to have an accurate map of guardrail damage, but other infrastructure analysis across the state of Alabama. And our naive plan started out with Python, right? Python can do anything. So we thought we would minimally process this data and then upload it to a database somewhere, and we just need to find a dashboard. And that would be our hardest challenge. It wasn't anything like that. We saw the need for edge compute in this situation. And what is edge compute and why is it on a truck? So for example, I'm going to illustrate edge compute in this way. If we've got engine data, so we know the engine's running, the truck is moving down the road. And we also can grab seatbelt safety information. So if the truck is driving down the road and the seatbelt is fastened, that is a state, that is a safe state, and nothing really needs to happen. We don't need to stream that information back to our database all the time, just logging that state. We want to cover the difference, or a condition of alert. So for example, if the vehicle's moving and the state changes in another system of the seatbelt is unfastened, that's the condition that we want to log, report, and take actions on. Another example is our real-time detection data. We don't want to stream 2 video feeds up to the cloud all the time, wasting cellular bandwidth, when these damage events are only going to be detected in a fraction of the frames. So we began looking for a platform to accomplish this goal. We definitely didn't want to go all the way to a managed and structured app, but we didn't really want to build out our own raw services either and manage all the DevOps tool chain on that. So we built a test harness with Python, and we just generated some sample data, randomized it, and we tested 4 or 5 different vendors and platforms. And we found good success with a platform called Locent. It gave us a way to have a modular edge workflow where we could apply business logic at the edge through version-controlled and predictable deployments, and also a cloud platform with a light database, management of the devices, and orchestration and dashboards. Here's a little more detail. So we've got all these systems talking directly or indirectly to the Locent Edge container out at the edge in the truck. And it bubbles up the data to events and states. So then we can also take the commands from the cloud and push it down to request control events, like to push data to the sign or other systems. So with our data platform in place, we move to the actual hardware. How do we get these containers running? So we boot up bare metal Kubernetes. We actually use K3s, had good success. Any K3s fans out here? Yeah. All right. We had good success. And we actually thought, we got this platform, we thought this was overkill. It had up to 6 cellular modems, SD-WAN, Wi-Fi, a switch with PoE with rugged connectors, and an i5 processor and 32 gigs of RAM for virtualization. And everything worked great. We even threw Argo CD on here for a GitOps style, and Keel was doing our image refresh hashes. There was a great question yesterday about the difference between Argo CD and Flux. And this was a good use case example. Because Argo CD, we ran the controller in the cloud, and our containers on here, our K3s, would register to the cloud and receive those deployments. This worked great until the bare metal, the cluster was offline. Argo CD doesn't deploy well to systems that are offline, and it won't retry. I know this because I opened an issue. It's still open after 2 years with a feature request enhancement on it. But still a great tool. But we reevaluated where to go from that. We looked at Flux. But at the moment, we're about to change platforms very soon. I'm going to spoiler alert there. But there was no ARM support for Argo or Flux v1 at the time. v2 was not out yet. Because this is a year or 2 behind. But the cool thing is we have our Kubernetes cluster and we're driving down the road. So this is my coworker's truck. He wired up the 4 cameras. It looks like a poorly underfunded startup Google Map competitor, and he got all sorts of questions. It was awesome. But you can see in the back, we've got all that gear laying around. But the cool thing is, all of our pipelines, our business logic, everything worked. The time that we spent running our sample test harnesses paid off. We had really good dashboards. And it was time to move to the machine learning side of our project. Now, this is funny because my family we spent our road trips and summer vacations, and I would be driving, and I'd see guardrail damage coming up ahead, and I'd say, quick, grab my phone. And they would take a little video. Because there's no commercial data set for guardrail damage. It doesn't exist. So the only way to get this information is to actually collect it myself. So after collecting a few hundred images and running it and training it through on a model, I was able to get just enough information, or just a functional model to find the anomalies. And now I can run, we upgraded to like a little GoPro. And so now we can take a little GoPro images and run that through and detect the guardrail with pretty good accuracy. But took a long time. And yes, this is what it turns out it generates for us. So we're able to run the camera through and find objects that are detected like guardrail damage. We have the image and the metadata, and we need to correlate this with the GPS coordinates at the edge, because, like I said, by the time you detect it and see it, you could be 100 feet behind it. So GPS coordination at the point in time when it's detected is very important. For those of you curious about machine learning models, we're using the YOLO V5 Nano. Now, not everything is perfect, and machine learning models are a good use case discussion for that, because it's all about confidence levels. So the machine has to rates the object with a certain confidence level. And you're going to get mistakes. You need to be able to filter these out from your end users. We obviously don't want to show our end users all these junk images. But the one on the bottom I found just a few days ago, and it cracked me up. And if you recognize this, this is the Huntsville Space and Rocket Center. And it's the SR-71. Cracked me up. So if you see ALDOT trying to tow that away and fix it, now you know why. We tried, back up a little bit to our hardware. We had a model now, and we needed to execute it. And we tried it out on our hardware, which we thought was overkill. It pegged the CPU out. It did not have a GPU. We tried Intel's OpenVINO, and we just couldn't get the performance. Pegging your CPU, your Kubernetes cluster, is not a good thing. Nothing ends well. So we had to ditch this hardware for this reason and some others. So we had to make a choice. We either double down on the x86 platform and get something bigger that we could drop like a PCI GPU in, or go down to more of the embedded NVIDIA route. And we went with this NVIDIA. Now this slide's not going to reflect the drama here, but the first thing you'll notice is ARM64, and this was a shock to the system. This is before the Apple M1 was released, and the ARM64 for the community and the Kubernetes environments was shockingly low. As I mentioned, Argo CD, Flux V1, Helm V2, V3 was still release candidate being developed. All these products that we depend on in the Kubernetes world were not available in the ARM platform. And this threw us for a loop. We even tried to mix the cluster. I even tried to mix the cluster by adding just a GPU node of ARM64 and x86. That does not work well. Don't do that. The manifest are not happy. But after we solved all those problems, minus the GitOps, we have 4 gigs of RAM. Any of you that's managed a Kubernetes environment with observability tools, you're probably going to shake your head and say, there's no way you're going to get all the tools on there. And it's not. This was not going to work out partly for that reason. We couldn't get our product and other tooling on there with the K3S. The next surprise at this lower level was the NVIDIA runtime. And this was a DevOps shock for us too, because previously, because of the way it works. So NVIDIA wants you to mount the local file system into the Docker container. They attach the GPU resources and combine it with your Docker. If you're reading between the lines here carefully, this creates a very tight coupling between your root file system that's flashed on the box and the GPU architecture and your Docker container that you're running. It's a challenge. It threw us for a loop. And unfortunately, we couldn't get the performance we wanted out of this one either. We got about 25 frames a second. Now, I forgot to tell you the performance that we need out of this, because we have 2 cameras. We're we're looking on both sides of the truck for damage. We want to get 30 frames a second on each camera. We want to get 60 frames per second total. Why? Because at 70 miles an hour, you're passing 100 feet of guardrail per second. So you need all those frames to inspect the infrastructure around you. This takes us, so we went up to the next level on the NVIDIA platform to the Xavier. This is an Advantech OEM'd version of Xavier, as Xavier is just sold as a dev kit. But it gave us 16 gigs of RAM, double the cores, ARM64 still, and a lot more GPU, tensor cores, CUDA cores. The DevOps, the DevOps twist here is that there's no SD card, the only way to flash this box, is USB flashing. You flip the cover off, remove the faceplate, and USB on the motherboard. That's a little bit hard to automate. This is the final assembly of the product, and this is the entire back seat of a Ford 350 commercial truck. Right? If anyone tells you that Edge is small, they have never done it. That is our Edge compute box there. We'll talk about all those other things in just a moment, but I want to relay a couple things about when you're going to the Edge that, flashing that box and support, because I've done it, I've personally had to travel to the truck and do this. You got to remove bolts and wires and power and take it off and take the faceplate off and bring an Ubuntu machine and plug into the back of to the motherboard. That's no fun. Nobody wants to do that. But there's also other practical issues for supporting an Edge-based product. If you've ever owned a house, you probably know that water gets places it shouldn't go, and it does. We've had cameras that got water into their cabling boots and caused chaos on cameras. Also, we're reading OBD2 data from the serial port, which means there's a cable that goes to the front of the engine. So this can be a little tricky when you're trying to support it because your technicians need to understand everything from a multimeter to the host operating system to the container to the application code to support it. This is quite a bit tricky. Now, all that other stuff on that page, if you ever think Edge Compute is just a simple, small box, again, think back to this slide, because we had to provide, we actually provided the communication platform for the truck, which means we provided the router, which connects to their enterprise SD-WAN environment, the switch to provide the PoE and the data communications of this truck. There's a wireless access point for hotspot access, and our Edge Compute box there. We also had to provide the electrical support because everything is running off 12 volts, and we have fuses and capacitors and deep cells and all that stuff. Let's take a look back at the final design in a little bit more detail too. So we actually had to pull from another language entirely. As we began processing the OBD2 data, it was coming off as byte level data in frame format. And Elixir with the circuits library turned out to be a really good language to pull that off and process it. And the rest of our Python containers are uploading data to the Redis and MQTT at the edge. The Locent Edge container subscribes to those events, and the Locent Edge communicates with the sign through SNMP directly. Those events bubble up to the Locent Cloud dashboard, and then we spun up a few resources in Postgres in Azure. In Azure for Postgres SQL with PostGIS, because our data turned out to be very time series related, but also very geospecific. And I'll show you that in a second. We're storing our images in the Azure blobs, and the dashboards on Locent, the built-in dashboards on most platforms, were great, but they were not prepared for a time series data of this style. So I wrote my own in Vue, and I'll show you that next. But it's querying both directions for authentication towards Locent, because Locent also offers authentication for perhaps your end users to use the platform, and towards the Postgres. This is a recent map of some guardrail damage in the Birmingham metro area. It's turning out pretty good. And what would it be without some final outcomes with a machine learning vision? So this is the dashboard I wrote. I mean, maybe I'm not the most CSS expert, but It's in view. There's a Google map, and you can actually click on it, click on markers, and see the historical events broken out by 1-minute drive-by events as the truck's analyzing infrastructure and detecting the guardrail. So wrapping up, I hope I've shared a few things about edge compute. I told you about the test harness, very valuable tool as you're evaluating where to send your edge data and how to see how the platform handles it. We've also talked about how AI and ML will really impact your project, and all the way from hardware to DevOps. And we talked a little bit about edge support. You need to simplify it as much as possible, because everything that goes wrong will go wrong. Thank you very much for your time. Hope you've enjoyed it.
Thank you, Jason. That was awesome. So can we ask you questions? Yes. I have questions.
Questions are good, yes.
Awesome. So anyone else have questions before? Okay, sweet. So I've had to do this on the edge with K3S specifically. I guess Rancher 2.5 did not exist with their GitOps platform before this, right, with Fleet? Was that the Rancher Fleet management? Yep. I talked to Rancher, and before, it was on the roadmap. They were almost there. It was not out yet for the fleet management, and we're reevaluating our deployment. I'm actually spinning up Git Flux, and I may test out that platform. Second question. Since you have a whole network there, what about plugging in, so as far as updates go, if you have a system like Fleet, or I guess Argo, I think can be configured to do this, where you can plug it in with you can plug in another machine with a specific IP address, and that machine could be your source for your GitOps. And so so I had a refinery do this where they would bring like a special secure machine that would travel with them, but they could just plug it in, and because it has a static IP address, have you guys looked into? So I forgot to mention that we had to write entire DevOps for all the other infrastructure. So that's a totally different chain. We automate the entire truck communications platform, including the security. And like you mentioned, I think with the static IP, so we're pre-configured with the MAC address and the static IP, when the DHCP and everything for the edge compute. So the edge compute is after the fact of the communication platform, pops in, and the whole system knows how it works. Does that answer your question? It does, thank you. So anybody else? And I don't know if you could tell, this is like a super interesting topic to me, but all right, so we have a small break. Thank you, Jason. Can we have one more clap for him? Thank you.